This is the beginning of a voyage, only fantasied when most of us were born. A voyage of exploration into space. Saturn, sailing downriver to a Florida cape. A chapter of a legend in the making even now. A legend being made by many dedicated Americans in all businesses and professions. By the National Aeronautics and Space Administration, the Marshall Space Flight Center, other NASA centers, and American industry, such as the Chrysler Corporation, manufacturer of the Saturn I first stage, and the Douglas Aircraft Company, who developed and built the second stage. This structure, the Vertical Assembly Building, stands on an island off a Florida cape once called Canaveral, but since renamed for John Fitzgerald Kennedy.
I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth.
Launch Complex 39 at Kennedy Space Center is one of many launch sites developed, built, and used by NASA to launch manned and unmanned peaceful explorations of space. A complicated business which presents scientific and engineering problems unheard of a few years ago. The liftoff of Saturn V and later rocket launch journeys into space from this launch pad will one day seem almost commonplace events to some who are living even now. This seems strange, considering how little time has passed since we began the rocket research and development program that will make these journeys possible.
Lock tank pressurizing.
On Launch Complex 34 at Cape Kennedy, not far from the Apollo Saturn V spaceport, the first Saturn I countdown began not too long ago, on October 27, 1961. 10 unmanned flights have been made by Saturn I launch vehicles. Each of Saturn I's 10 missions took another cautious, necessary step toward extensive manned space exploration, not just of the moon, but even deeper into space. And only 16 years before, the research and development program responsible for Saturn I's success was just beginning in this country. And so, before the drama of the first Saturn launch begins, it might be well to understand its full significance, to see how deeply the roots of Saturn lie in the history of rocket flight. In these early years, there were several groups doing research to develop useful rocket vehicles. Even as today, the information gained was freely exchanged, rapidly extending the base of our knowledge, developing new technology, creating experience and skills from which we might ultimately move to spaceflight. From one of these groups came the first true spaceflight in the world. On February 24th, 1949, a WAC corporal placed a payload outside of the Earth's atmosphere. As these groups continued to extend this country's rocket technology, more room was required, and rocket researchers began to spread over the United States. In 1950, the Army Research Group moved to Redstone Arsenal, Huntsville, Alabama. Here, the successful Redstone and Jupiter missiles were developed by the United States Army. The Redstone and Jupiter, the grandfather and father of the Saturn. For during their development, the scientific base and technological know-how necessary for Saturn I were obtained. In 1957, this knowledge was already being used as men were sketching a vehicle designed from the ground up for lifting the tons of payload required for scientific space exploration. Predicting the need for a booster with 1.5 million pounds of thrust, these rocket scientists said This need could be met with a cluster of existing Redstone and Jupiter tanks and Jupiter rocket engines, plus many hours of engineering work to tie them together. But in the fall of that year, the Soviets launched Sputniks 1 and 2. Long-range projects were temporarily shelved. On January 31st, 1958, only 6 weeks after Sputnik 2, the first American satellite, Explorer 1, was placed in orbit by Juno 1, a modified Redstone with a thrust of 83,000 pounds. Its payload discovered the Van Allen radiation belt. With our own capability in space an established fact, on July 26, 1958, ARPA, the Advanced Research Projects Agency, approved the program for a clustered engine booster with 1.5 million pounds of thrust. A single engine powerful enough to produce this thrust was under development by American industry in 1958. But neither this engine nor its tanks would be available in time. Besides, with 8 well-proven, properly clustered smaller engines, the failure of one would not mean the failure of the booster to lift its heavy load. The clustering of already designed Jupiter and Redstone hardware would save both time and money as we moved ahead. On August 15, 1958, the Saturn project was assigned to the experienced group that had developed Redstone, Jupiter C, Juno 1, and launched the Explorer satellites. It was a team geared to conduct its own research, development, and production. Its highly successful products were literally custom-made in its own laboratories, shops, and offices, or produced to specification by a relatively few major industrial contractors. But where only pounds had been lifted before, tons of weight would be blasted into orbit to explore space, in which we had only begun to pioneer. The lightweights were having their day. Soon it would be time for the heavyweights. It was time for Saturn I, and in July 1958, NASA was born. 6 months later, the Saturn project, along with other Army space-related missions, became part of the NASA program. The size and complexity of Saturn I, the size of the booster alone, and the complexity of its components presented an enormous technical and scientific challenge. Another challenge would be presented by the larger complexity of the management and organization required to sustain a number of other space projects already underway in 1958, and yet move on beyond the frontiers of science and engineering. To produce a series of huge Saturn I rocket boosters in a mere handful of years, and to ensure success, would create a revolution in both management and engineering development. Early in 1959, it was decided to use the liquid propellant H-1 engine, an improved version of the S-3 Jupiter and Thor engine developed by Rocketdyne, as the basic element in the Saturn engine cluster. Fabrication and assembly of a ground test first stage to prove out the cluster tank and engine concept was started in mid-1959. Translating this concept into a working vehicle required proving out new ideas, for there were many engineers and scientists who had doubts that 8 rocket engines could be fired at the same time in close proximity, or that 9 propellant tanks could be fastened together so they would not shake apart during flight. The second stage, designed and developed by the Douglas Aircraft Company, would be powered by 6 liquid hydrogen-oxygen engines. Selected for its greater thrust per pound of fuel, the super-cold liquid hydrogen would require NASA and industry to develop a new technology. Much is always made of space technology. The hardware is glamorous. But little is known of the management program that makes a number of complex projects simultaneously possible. 3 main projects ran like nerves through the Saturn program: development of the launch vehicle, development of ground support equipment, and the development of launch facilities. Each demanded sustained and intensive effort. Each was a separate project, yet interrelated with the other two. Through 1960 and into 1961, the Saturn program continued, developing not only the first flight vehicle, its engines, equipment, and instrumentation, its plumbing, and its circuitry, but also providing for support and launch facilities. While the booster was being developed, modification began to a static test stand at Huntsville, Alabama, to captive fire the first stage. It took a year to convert the 177-foot-high structure. When it was finished, a mock-up was installed to check the fit and test out methods for servicing the booster during static tests. These static tests began in March 1960, first with 2. Then with 4. Finally, many weeks later, with all 8 engines running. Then came another change in the management of the Saturn I program. In September 1960, that part of Redstone Arsenal transferred to NASA was formally dedicated as the George C. Marshall Space Flight Center. President Eisenhower had long ago stated his belief that outer space should be used for peaceful purposes. Aeronautical and space scientific activities sponsored by the United States should be, he said, under the direction of a civilian agency. Now, this was an accomplished fact, and the President had this to say.
We are propelled in these efforts by ingenuity and industry, by courage to overcome disappointment and failure, by free-ranging imagination, by insistence upon excellence. In this fact is proof again that hard work, toughness of spirit, and self-reliant enterprise are not mere catchwords in an era dead and gone. They remain the imperatives for the fulfillment of America's dream. Not push buttons, nor electronic devices, but superlative human qualities have brought success and fame to this place.
In that fall of 1960, the planning and construction continued. New test stands at Marshall and at contractors' facilities, launch and ground support construction at the Cape. Meanwhile, transporters to haul the bulky boosters from place to place. Aircraft to ferry the bulging second stage and other cargo from coast to coast. Barges to float the first stage down the river and through the Gulf. These and thousands of other items, large and small, had to be provided for Saturn I. With so much happening, new information flowed almost constantly into the Saturn project. New technical fields were explored, new techniques devised for assembly, fabrication, and other processes. New decisions were made. In early 1961, the Saturn I prime mission was changed from launching scientific satellites to supporting the growing manned spaceflight program. The first stage, therefore, had to be redesigned to include fins for additional stability, larger propellant tanks, and uprated engines for heavier payloads of about 10 tons as compared to the 20 pounds of Explorer 1. Guidance and control instrumentation was also moved at this time from the separate stages and combined into a single instrument unit. As new technology advancements were made, and as scientific breakthroughs were achieved, change was a constant factor all through the years of Saturn I development and flight. For these were the years in which valves, pumps, tubing, turbines, tanks, engines, gyroscopes, accelerometers, and computers, all adapted to the rocket environment, were developed and produced. This created a vast array of instruments, pressure and strain gauges, transducers, telemeters, beacons, and recorders. The combination of high stress, heat, and vibration demanded creating new alloys of steel and aluminum, increased the use of other metals, beryllium, titanium, molybdenum, and tungsten. The same physical properties making these metals suitable for Saturn also required development of new methods of working them. So, new tools based on the latest engineering theory and scientific discoveries were developed. Magnetic forming, chemical milling, electron beam welding, to name a few. Ground service equipment was developed and produced for test stands and launch sites springing up like wildcat wells. Liquid fuels, some commonplace but others once considered rare and exotic chemicals, were produced by tons: kerosene, liquid oxygen, and hydrogen. Liquid hydrogen technology, the development of techniques for the manufacture, delivery, storage, and use of the super-cold liquid hydrogen with its minus 423-degree boiling point, reached a scale never attempted before. The engineering and research lay on the edge of the state-of-the-art throughout the program, and the skills involved were more diversified than usual. No single government agency, or even the entire government, could command all the knowledge and skills needed. Rather, a combination of government, educational institutions, and private industry was needed. This led to increasing industrial support for the Saturn I program. More and more corporate names began to appear on tools and equipment, on containers, on small parts and components developed in industrial plants scattered across the United States. More and more names appeared on office doors and building walls, on the smocks of engineers and technicians. At the same time, there was another shift in Marshall's philosophy of vehicle development, a shift from the basic concept of testing vehicles in flight to the idea of testing not only all components, but the vehicles themselves in ground test facilities, even though these also had to be designed and built. The reasons for the shift from flight to ground testing were mainly economic. Flight testing required a large number of expendable flight vehicles. The Jupiter program alone had involved almost 50 flight test vehicles. But the high cost of each Saturn I set a definite limit on the number of these that could be launched simply for test purposes. And everything happened everywhere at once. In Florida, machinists formed parts for a liquid hydrogen rocket engine. While in Tennessee, wind tunnel blasts roared past a scale model of the Saturn vehicle. While in California, the dome of a Saturn fuel tank turned on a welding fixture. And in Huntsville, at the same time, a full-sized Saturn first stage shook in its test stand. The use of mock-ups, special stages, flight stages, computers, special test stands, and other ground test facilities reached the point in the Saturn I program where the success factor for any given vehicle was exceptionally high. Success in flight was almost guaranteed, in fact, by the continuous, growing, and cumulative effect of testing on the ground. Research, design, develop and test. Assemble and test and modify. Test, reassemble and test, and mate and test, and modify, and test again. This was the pattern resulting in Saturn's reliability, a pattern that flowed through months and even years of constant change and growth and new research that often began the cycle over again. Finally, not somehow, but as the result of management grounded in science and technical competence, the reliable parts, components, systems, and stages of Saturn I were joined. In August 1961, the first Saturn flight vehicle was ready for shipment from Marshall to the Cape. Its stages and payload body moved from Marshall shops to docking facilities on the Tennessee River for loading aboard the barge Palaemon. On August 5th, the barge began its slow trip downriver, through the Gulf of Mexico, and around the Florida Peninsula to the Cape. There, the stages were unloaded. Assembly of the first flight vehicle began in the middle of August. Towering 162 feet on its launch pedestal at Launch Complex 34, loaded with propellants, its weight on liftoff totaled 460 tons. Before that happened, however, other matters were attended to. On September 13, 1961, contracts were let for the Army Corps of Engineers to build Launch Complex 37, an additional Saturn I launch complex. At Marshall, designs were being drawn of bigger and more advanced Saturn vehicles to launch manned explorations of the moon and deeper space. In October, NASA acquired Michoud Ordnance Plant at New Orleans. Here, in this manufacturing facility, Chrysler would build the last two Saturn I first stages, and Chrysler and other NASA stage contractors would build first stages for more advanced Saturn vehicles. Out west, an upper stage manufacturing and assembly site for advanced Saturn vehicles was planned for Huntington Beach, California by Douglas Aircraft Corporation. Such planning extended into the years ahead. For the launch of the first Saturn vehicle from Launch Complex 34 on October 27, 1961, the Saturn I and advanced Saturn flight programs were only beginning.
1, 0. Ignition. All engines running. Launch commit, liftoff.
The first Saturn launch was almost flawless. None of the 10 flights presented significant problems. The prime mission of the first 4 Saturn flights was to verify first stage design and prove out launch facilities. There were some distinctive differences, however, between these early flights. A secondary mission was assigned to SA-2 and 3, Project Highwater. 95 tons of water ballasting the dummy second stage was deliberately exploded in space to see what effect this would have on the ionosphere. The explosion caused only a temporary disturbance. SA-3 also carried the first full propellant load of 750,000 pounds. A secondary mission for SA-4 was the testing of its engine-out capability. One engine was cut off in flight to see if the vehicle would operate on the remaining 7. This it did, scoring the 4th Saturn I success. On January 29, 1964, NASA launched the 5th Saturn I. The liquid hydrogen-fueled second stage, flight tested for the first time, functioned perfectly. First stage engines shut off as planned. Onboard cameras recorded second stage separation and ignition. The stage's engines burned for 8 minutes, and with attached instrument unit and sand-filled nose cone, attained orbit as an Earth satellite. This almost 19-ton satellite was the heaviest ever orbited by the free world. SA-6, launched 5 months later on May 28, 1964, was the first to place into orbit an Apollo boilerplate command and propulsion module. The Apollo spacecraft is being developed by the Manned Spacecraft Center, Houston, Texas. There was another first for SA-6, activation of a new guidance system. This system, developed at Marshall, was unique and complex, fully exploiting the state-of-the-art. It was designed to constantly monitor the flight path and compute completely new trajectories as the flight progresses. This guidance system, active for the first time on the 6th flight, successfully corrected an unexpected deviation from the planned trajectory caused by the premature shutdown of one engine. As a result of this kind of excellent performance, SA-6 was the last Saturn I R&D vehicle instead of SA-10 as originally scheduled. The rest would be operational vehicles. On September 18, 1964, SA-7 launched the second Apollo boilerplate spacecraft into orbit, testing its structure and design and demonstrating its compatibility with the launch vehicle. All other major test objectives of this flight were also met. SA-9 placed in orbit the first Pegasus, a meteoroid technology satellite, on February 16, 1965. Pegasus, developed for NASA's Office of Advanced Research and Technology by Fairchild Hiller Corporation under the management of Marshall, was shrouded by the Apollo boilerplate command and propulsion modules. Onboard television recorded shroud ejection after second stage shutdown. Then Pegasus extended its 100-foot aluminum-plated electronic wings and, like a moth emerged from its cocoon, moved on, its wings spread to measure and report the hazards of meteoroids in space. Data from Pegasus confirmed that the Apollo spacecraft design is adequate to protect astronauts from meteoroids. SA-8, launched at night, orbited the second Pegasus satellite. SA-10, the final Saturn I flight vehicle, launched Pegasus III. The 10-vehicle Saturn I program was without precedent in the history of spaceflight.
8 PSI. VCR, continuous light on. 10 PSI on lock tank. VCR, continuous light on.
Each vehicle of the program established new levels of rocket reliability far above those of 16 years earlier.
42 fast. 42 and a half, 43. 8 KPI disconnected. 45. Lock tank pressurized.
A program providing the foundation for the follow-on advanced Saturn programs, the uprated Saturn I and Saturn V.
Sequence retracted.
4, 3, 2, 1, 0.
Ignition. All engines running. Thrust commit. Launch commit. Lift off. Go.
That's the story of the first 10 lives of Saturn I, each one an essential step in the development of large launch vehicle science and technology. Each flight a vital step toward the future of man's extensive exploration and utilization of the universe for the benefit of the entire human race.